Welcome to Module 14, Sensors and Measurement Systems. In building automation, a sensor is often treated like a small component, but it is actually the beginning of a decision chain. A temperature value, a pressure value, a flow value, or a CO2 value can start an alarm, change a sequence, open a valve, reset a set point, or send a team into the field. In this module, we will evaluate the complete measurement chain from the physical condition to the sensor to the transmitter, wiring, controller input, trend, alarm, and final decision. The goal is simple. Do not trust a number just because it appears on a screen. Verify the chain before you act. By the end of this module, you should be able to evaluate sensors as part of a complete measurement system. We will look at sensor type, range, installation, wiring, controller input, calibration, trend behavior, and decision impact. The key point is that a good-looking BAS number is not automatically a good measurement. If a value is used for safety, comfort, efficiency, compliance, or troubleshooting, the BAS professional must understand how that value was created and how reliable it is. This visual shows the measurement chain. First, there is a physical condition: temperature, pressure, airflow, humidity, CO2, current, or status. Then the sensor element detects that condition. The transmitter or interface converts the signal. Wiring and communication carry it to the controller. The controller scales and processes it. Then the value appears in trends, alarms, graphics, analytics, and reports. Finally, someone makes a decision. If any link in this chain is weak, the decision can be wrong. That is why we evaluate the chain, not just the sensor specification. Sensor selection begins with the application. A space temperature sensor, a duct averaging sensor, an immersion sensor, and a surface sensor are not interchangeable. Pressure sensors are even more sensitive to range and reference location. A transmitter can be accurate on paper and still be a bad choice if the expected measurement is only a small fraction of the device range. In the field, ask whether the sensor is measuring the right physical condition in the right location with a range that supports the decision being made. A measurement can look precise without being accurate. For example, a room sensor may display 72.04 degrees, but if it is installed on a sunlit wall or behind a cabinet, the extra digits do not make the value trustworthy. Accuracy tells us how close the reading is to the true condition. Precision tells us how repeatable it is. Resolution tells us the smallest increment we can see. Drift tells us the value may slowly move away from truth. For important decisions, do not only say what the BAS value is, say how much confidence you have in it and why. Sensor location is one of the most common reasons a BAS value is misleading. A perfect sensor on the wrong wall can create comfort complaints. A duct sensor after a mixing box can be useless if the air is still stratified. A room pressure transmitter can be accurate but false if the reference tubing is exposed to wind or block. When you troubleshoot, do not only ask whether the sensor is calibrated, ask whether that sensor is located where it can see the condition the control sequence assumes it is measuring. Verification and calibration are often used as if they mean the same thing, but they are different. Verification is a field confidence check. We compare the BAS value to a trusted reference and ask whether the result is close enough for the decision. Calibration is a formal adjustment to a standard, usually with a defined procedure and record. Functional testing goes one step further. It confirms that the measured value produces the correct alarm, trend, lockout, or control action. A BAS professional should know which activity is needed before calling the measurement good. Temperature pairs are used everywhere in BAS diagnostics: supply and return water, entering and leaving air, mixed and outdoor air, and coil entering and leaving conditions. The danger is that load calculations depend on the difference between two values. If one sensor is biased by only 1 or 2 degrees, the percentage error can be large when the delta T is small. Before making decisions from calculated load, verify the sensor pair together under the same conditions. The question is not only whether each sensor is good by itself, but whether the pair is good enough for the calculation. Most BAS pressure values are differential measurements. Duct static pressure, filter pressure drop, hydronic differential pressure, and room pressure all compare one location to another. That means the reference is part of the measurement. If the high and low sides are reversed, if tubing leaks, if a line fills with water, or if the reference is exposed to wind, the value can be false. Do not stop at transmitter calibration. Verify the tubing path, reference location, range, zero, and the physical condition being measured. Many BAS values are not raw measurements. Dew point is often calculated from temperature and relative humidity. Airflow may be calculated from differential pressure and a calibration factor. Cooling tons may be calculated from flow and temperature difference. Plant efficiency may depend on multiple meters. When a calculated value looks wrong, do not start by changing the formula or the sequence. Identify every input, then test the weakest input first. A bad calculated value is often caused by one poor measurement, one wrong scaling factor, or one hidden assumption. Every sensor-dependent sequence should have a known failure behavior. What happens if the sensor is open, shorted, out of range, frozen, drifting, or lost on the network? Some failures are obvious. Others are dangerous because the value remains plausible. A humidity sensor that slowly drifts high may cause unnecessary dehumidification. A pressure value that freezes during communication loss may keep a fan running with false confidence. For important measurements, define the fallback behavior, alarm the condition, and document how the system should respond when confidence is lost. Verification should be repeatable. Start by defining the decision. A sensor used only for display is different from a sensor used for freeze protection, pressure control, or energy reporting. Then identify the chain. Compare the BAS value with a trusted reference at the real sensing location. Check response if the condition can be changed safely. Finally, document your confidence. What you measured, what instrument you used, what the readings were, and what decision is supported. This is how sensor troubleshooting becomes professional evidence. The sensor confidence model is a practical way to decide whether a measurement is strong enough for action. Look at application fit, range, location, installation quality, verification status, trend behavior, and decision risk. If confidence is high, the value may support action. If confidence is medium, verify before making a major change. If confidence is low, investigate the measurement chain first. The same sensor reading may be acceptable for operator awareness, but unacceptable for a critical alarm or automatic reset. Here is a realistic field problem. A laboratory room pressure trend looks stable, and the transmitter calibration record looks acceptable. At first glance, the team assumes the room is performing correctly. But the reference tube terminates above the ceiling near a return air path, so the reading does not represent the corridor reference the sequence assumes. The sensor was not simply bad. The measurement chain was wrong. The professional response is to verify the reference location, door behavior, supply and exhaust flow, leakage path, alarm delay, and trend behavior before accepting the value. The correct answer is C. The coil may have a real performance issue, but the first professional step is to verify the evidence. Check paired temperature sensors, flow measurement, sensor location, scaling, operating state, and uncertainty. A 100% valve command tells us the BAS is asking for full output. It does not prove that the flow is correct, the temperature pair is accurate, or the calculated load is reliable. Evidence comes before equipment replacement or sequence edits. For the assignment, select one critical BAS value and map the full measurement chain. Do not stop at the sensor model number. Identify the physical condition, sensor type, range, location, wiring or tubing, controller input, scaling, trend behavior, and decision impact. Then verify the value with a trusted reference when possible and assign a confidence rating. The module takeaway is simple. Strong BAS decisions require strong measurement confidence. Next, we will move from sensors to actuators, valves, and dampers, where we verify that commanded action actually produces physical movement and the intended outcome.